So in this lecture now we're going to talk about more allylic stabilization of carbanions in the case of organometallics specifically. So consider this primary allylic bromide that is going to undergo reaction of oxidation or oxidative type insertion with magnesium in an ether aprotic solvent. Of course, this is necessary for formation of an organometallic. So magnesium starts in the zero oxidation state, and upon reaction with the bromide, magnesium inserts into the carbon-bromine bond, and the effective oxidation state now of bromide is still -1, but the carbon has been reduced to -1, and magnesium, the less electronegative atom, is +2 in its alkaline earth metal oxidation state. So, of course, there's a bond dipole between carbon and magnesium where the carbon is much more electronegative, right? The electronegativity value of carbon is about 2.5, while the electronegativity value of magnesium is much lower. It's about 1.2. So the bond dipole points towards carbon. Or another way, we can sort of treat the sigma bond as being a lone pair. Or you can think of this allylic magnesium bromide as really being a carbanion type intermediate, where that negative charge sits on the carbon atom, and then magnesium bromide sits here as a counterion. Where collectively the -1 and +2 add to give a +1 net charge for this salt. So think of Grignard reagents and organolithiums, etc., as being carbanion-like, where that carbon-magnesium bond is so polarized that we can approximate it as a primary carbanion. And of course, this is a primary allylic carbanion. Now, there's some interesting reactivity of these because when that carbon is allylic, we can show this as either resonance form, or we can push this lone pair down to form a pi bond, and then push the adjacent pi bond over to form a lone pair. So we can show that pi electron density delocalizing, and then a lone pair arrives at the secondary position. And magnesium bromide, of course, would sit next to that secondary carbon to stabilize the negative charge. So this carbanion is secondary allylic. And so upon reaction with an electrophile, like epoxides, we know that Grignards undergo epoxide opening reactions. Either the primary allylic nucleophilic atom or the secondary allylic atom can undergo attack, or I should say, can attack the epoxide through nucleophilic addition. And that mechanism looks like this, where either carbon of the epoxide can be attacked through SN2, and then the epoxide opens. Same mechanism for epoxide opening with the secondary allylic carbanion. So this is going to lead to a couple products. There's 2 new carbons, and then an O- after opening the epoxide. Where the carbons of the epoxide are these 2, and the new alkoxide intermediates. So we get 2 different regioisomers, and upon neutralization with strong acid, of course, they'll protonate to become 2 distinct primary alcohols. And these two primary alcohols are each structural isomers of one another or are regioisomers. And so which product predominates depends on the regioselectivity, which comes down to arguments of kinetic and thermodynamic control. We won't go into those too much with this allylic anion example. It's a bit more complex than the cation we discussed in a previous video, but I just want you to know that both products can form because this Grignard is on average more stable than your average Grignard because it's stabilized by two resonance forms or resonance stabilized. And we can explain that by drawing the hybrid molecule to show that that carbanion is delocalized and it's not as basic as a typical carbanion that lacks resonance. Here there are 3 carbon atoms that are participating in pi bonding, and there's negative charge on both carbon 1 and carbon 3. The major resonance structure, or the more stable one, is the less substituted carbanion, right? That's the opposite of carbocation stability, right? Tertiary cations are most stable, but primary anions are most stable because these carbons do not want neighboring CH bonds to hyperconjugate with them. They're already filled orbitals, and therefore carbanions are more stable at less substituted positions. The minor resonance structure is the one that has the less stable double bond and the more substituted carbanion, the secondary. So that's why I've shown less negative charge here. But they're both nucleophilic carbons. And that's why either one of them can attack the epoxide, the electrophilic species, to create a variety of alcohols. So we get this sort of rearrangement type reaction where the alcohol can form as either one of 2 structural isomers. So be careful with allylic Grignards. They often give multiple products, and also they have decreased basicity because of stabilization of the carbanion or the negative charge. So we'll examine this with a benzylic and allylic case where I take a primary chloride, which can also react with lithium to give this alkyl lithium intermediate. Now, 2 equivalents of lithium are required because lithium is an alkali metal or only takes on a +1 oxidation state. The carbon now has been reduced to -1. Lithium bromide is the side product, or excuse me, here it's lithium chloride, but alkyl chloride, bromide, or iodide could be used. And so because we get this side product of a lithium chloride salt, that's why we need 2 equivalents of lithium. Lithium only makes 1 bond instead of magnesium, which made 2 bonds and simply did an insertion. So we can now treat this as a carbanion, just like we did the Grignard in the last example, where we simply think of this carbon-lithium sigma electron density as being sort of like a lone pair on that primary carbon with negative charge on that carbon, and the lithium sits nearby as a counterion. And that's because, of course, the bond dipole between carbon and lithium is very much pointed towards carbon, or there's a great deal of negative charge on carbon and positive charge on lithium. So this carbanion is sort of the extreme of that, right? The electronegativity value of lithium is even lower than magnesium. It's only about 1. And carbon is far more electronegative. 2.5 is its electronegativity value. So this is a primary allylic carbanion that is resonance stabilized. So just like in the last example, we can show resonance structures, and I'll show the hybrid. So you'll be able to draw a total of about 8 resonance structures for this compound. And because this lone pair is allylic, we can delocalize that lone pair to form a pi bond. And it turns out all of these carbons in this molecule are conjugated together, sharing pi electron density. And the negative charge is on the primary carbon primarily, but you can also push that lone pair onto this carbon atom to show negative charge here. Or you could push the lone pair onto the benzylic carbon like that to show negative charge there. And then once it's benzylic, then you can delocalize it around the ring, and the negative charge will land on the ortho and the para positions only. So there are actually 8 resonance structures total, and the weighted average of those gives this hybrid molecule. Which means that when you undergo a subsequent reaction with D2O, right, this is just deuterated water, then we're going to get an acid-base reaction. And D2O could protonate any of these carbons that are electron rich and basic. So there's a total of 6 carbanion-like or basic carbons. So upon protonation with D2O, you can get the deuterium on the primary position that comes from protonating this lone pair. You could also get deuterium on the secondary position that comes from protonating the secondary carbanion. You could get it on the benzylic position right here. That comes from protonating this carbanion that's secondary benzylic. Or you could get deuterium protonating the actual aryl ring, but this product here is least likely. And the reason that one's least likely is because the starting material has this stable aromatic 6-membered ring with an odd number of pairs of pi electrons in the ring. And the product now still has a hydrogen there at the newly deuterated carbon, but that means that this carbon is now sp3. And therefore, the entire ring is no longer conjugated, or it's a non-aromatic product. And forfeiting aromaticity is going to be what causes that product to be least likely. A through C are all still aromatic rings, where we have the cyclic pi system with an odd number of pairs of pi electrons and all sp2 atoms. So these carbons of the benzene ring, the ortho and para position, do take on some negative charge and help to stabilize the intermediate and decrease its basicity. However, they're unlikely to undergo a net reaction because that would involve forfeiting aromaticity or making the product non-aromatic. So you should be able to understand the reactivities of these organolithiums and Grignards and draw all of the allylic resonance structures where that lone pair skips one atom at a time and the negative charge is delocalized throughout every other position. But then also understand that it's the exocyclic carbons, those outside of the aromatic ring, that are most likely to undergo reaction, because those will facilitate the formation of products that retain aromaticity with this benzene ring undergoing no change. So for more practice with organometallics and with anionic stabilization at allylic and benzylic positions, you can visit either my Organic 1 or my Organic 2 course guide, and both of those are available at chemguides.com.